Dual feed or loop feed is a strategy used to provide redundancy in the event of a transformer failure. In this configuration, the utility uses two transformers to feed the same service drop. The idea is that if one transformer fails, the other will continue to provide power. However, this strategy can also lead to unbalanced currents in the line. The two transformers are unlikely to be perfectly matched, so they will not deliver the same amount of current. This imbalance can create magnetic fields. A suitable fix is to feed from just one transformer. This eliminates the unbalanced currents and the resulting magnetic fields. When current flows through a conductor, it creates a magnetic field around that conductor. The strength of the magnetic field is proportional to the amount of current flowing through the conductor. In a balanced three-phase system, the currents in the three phases are equal in magnitude and 120 degrees apart in phase. The magnetic fields created by the three phases cancel each other out, resulting in a net magnetic field of zero. However, if the currents in the three phases are not equal, the magnetic fields will not cancel each other out, resulting in a net magnetic field. This is what happens when there are unbalanced currents in the line. The unbalanced currents create a net magnetic field, which can then radiate into the surrounding area. In the case of a house with an unusually high magnetic field, the unbalanced currents in the line were creating a magnetic field that was radiating into the house. The utility's fix of feeding from just one transformer eliminated the unbalanced currents, which in turn eliminated the magnetic field. Electrical current always seeks the path of least impedance back to its source. Impedance is the total opposition to current flow in an alternating current circuit encompassing both resistance and reactance. In a typical electrical distribution system, the neutral conductor is grounded at multiple points. This creates multiple paths for the neutral current to flow back to the source. Ideally, the neutral current should be evenly distributed among these paths. However, if the impedance of one path is significantly lower than the others, a disproportionate amount of neutral current will flow through that path. This can happen if there are poor connections, corroded conductors, or other issues that increase the resistance of some paths. High currents in water pipes can be indicative of a problem with the grounding system. Water pipes are often used as a supplemental grounding electrode, but they should not be the primary path for neutral current. If a significant amount of neutral current is flowing through the water pipes, it means that there is a problem with the main grounding electrode or the neutral conductor. This can create a shock hazard and can also damage the water pipes. The utility company's service drop neutral connections are critical to the proper functioning of the electrical distribution system. If the neutral connections are loose or corroded, it can create a high impedance path for the neutral current. This can cause a variety of problems, including voltage drops, flickering lights, and increased magnetic fields. The utility company should regularly inspect and maintain the service drop neutral connections to ensure that they are in good condition. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. Grounding is the process of connecting the electrical system to the earth. Bonding is the process of connecting all of the metal parts of the electrical system together. Grounding and bonding are essential for safety. They help to protect people from electric shock and help to prevent fires. The NEC requires that all electrical systems be grounded and bonded in accordance with specific requirements. These requirements vary depending on the type of system and the application. Some relevant NEC sections include 250.4, which covers general requirements for grounding and bonding, 250.24, which covers grounding of service equipment, 250.50, which covers grounding electrode systems, 250.104, which covers bonding of metal water piping, and 300.3, which covers conductors of different systems. Understanding these sections of the NEC is essential for ensuring the safety and proper functioning of electrical systems. When troubleshooting EMF issues related to electrical systems, it is important to consider all possible sources of magnetic fields. These sources can include unbalanced currents, ground loops, and improper wiring. Unbalanced currents, as discussed earlier, can create significant magnetic fields. Ground loops occur when there are multiple ground paths in a circuit, creating circulating currents that generate magnetic fields. Improper wiring, such as running hot and neutral wires separately instead of bundled together, can also create magnetic fields. A thorough investigation of the electrical system is necessary to identify and address all potential sources of EMF. This may involve measuring currents, voltages, and magnetic fields at various locations in the system. It is also important to visually inspect the wiring and grounding system for any signs of problems. In some cases, it may be necessary to consult with a qualified electrician or EMF consultant to resolve complex issues. Remember, working with electrical systems can be dangerous, and it is important to take all necessary safety precautions. Always to energize circuits before working on them and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work for you. Electrical systems are designed to operate within certain voltage and current limits. Exceeding these limits can damage equipment and create a safety hazard. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical systems from overloads and short circuits. These devices will automatically trip or blow if the current exceeds the rated value. It is important to ensure that the overcurrent protection devices are properly sized for the circuit they are protecting. Using an overcurrent protection device that is too large can allow excessive current to flow, which can damage equipment or start a fire. The NEC provides detailed requirements for overcurrent protection in Article 240. This article covers the selection and installation of overcurrent protection devices for various types of circuits and equipment. It is important to understand these requirements to ensure that electrical systems are properly protected. In addition to overcurrent protection, electrical systems also need to be protected from ground faults. A ground fault occurs when a hot wire comes into contact with a grounded surface, such as a metal enclosure or a water pipe. This can create a dangerous shock hazard. Ground fault circuit interrupters, or GFCIs, are designed to protect people from ground faults. GFCIs will quickly trip and energize the circuit if a ground fault is detected. The NEC requires GFCIs to be installed in certain locations, such as bathrooms, kitchens, and outdoor areas. These locations are more likely to have wet conditions, which increases the risk of ground faults. Understanding the principles of electrical safety is essential for anyone working with or around electrical systems. This includes understanding the hazards of electricity, how to protect yourself from electric shock, and how to properly use electrical equipment. It is also important to be aware of the NEC and other applicable codes and standards. By following these guidelines, you can help to ensure the safety of yourself and others. Electrical distribution systems are complex networks that deliver power from the generating station to the end user. These systems typically consist of substations, transmission lines, and distribution lines. Substations are used to step down the voltage from high voltage transmission levels to lower voltage distribution levels. Transmission lines are used to carry power over long distances. Distribution lines are used to deliver power to individual homes and businesses. The design and operation of electrical distribution systems is a complex engineering discipline. Electrical engineers use sophisticated software tools to model and analyze these systems. This helps them to ensure that the systems are reliable, efficient, and safe. The reliability of electrical distribution systems is critical to modern society. A power outage can disrupt businesses, schools, and hospitals. It can also create safety hazards. Utility companies invest significant resources in maintaining and upgrading their electrical distribution systems to minimize the risk of power outages. This includes regular inspections, preventative maintenance, and the replacement of aging equipment. They also use advanced monitoring and control systems to detect and respond to problems quickly. The efficiency of electrical distribution systems is also important. Energy losses in these systems can be significant. Utility companies are working to reduce these losses by using more efficient equipment, such as transformers and conductors. They are also implementing smart grid technologies such as advanced metering infrastructure, or OMI, to better manage energy demand. The safety of electrical distribution systems is paramount. Utility companies have strict safety procedures in place to protect their workers and the public. These procedures include the use of personal protective equipment, or PPE, and the implementation of lockout-tagout procedures. They also provide training to their workers on electrical safety. Harmonics are distortions of the sinusoidal waveform of alternating current or voltage. They are caused by nonlinear loads such as electronic devices and variable frequency drives, or VFDs. Harmonics can cause a variety of problems in electrical systems, including overheating of equipment, increased energy losses, and interference with communication systems. Harmonic filters can be used to reduce the level of harmonics in electrical systems. These filters are typically installed at the point of common coupling, or PCC, where the nonlinear loads are connected to the electrical system. Power factor is a measure of how effectively electrical power is being used. It is the ratio of real power to apparent power. Real power is the power that is actually used to do work. Apparent power is the product of voltage and current. A power factor of 1 indicates that all of the power is being used to do work. A power factor of less than 1 indicates that some of the power is being wasted. Low power factor can cause a variety of problems, including increased energy losses, reduced equipment capacity, and voltage drops. Power factor correction capacitors can be used to improve power factor. These capacitors are typically installed at the load or at the point of common coupling. Voltage regulation is the ability of an electrical system to maintain a stable voltage level under varying load conditions. Voltage drops can occur when the load in the system increases. Excessive voltage drops can cause equipment to malfunction or fail. Voltage regulators can be used to maintain a stable voltage level. These regulators are typically installed at substations or at the load. Transient voltage surges are short-duration high-voltage spikes that can occur on electrical systems. These surges can be caused by lightning strikes, switching operations, or equipment failures. Transient voltage surges can damage sensitive electronic equipment. Surge protective devices, or SPDs, can be used to protect equipment from transient voltage surges. These devices are typically installed at the service entrance or at the equipment being protected. Electrical grounding is the process of connecting the electrical system to the earth. Grounding provides a lower impedance path for fault currents to flow back to the source. This helps to protect people from electric shock and helps to prevent fires. Grounding is required by the NEC. Bonding is the process of connecting all of the metal parts of the electrical system together. Bonding helps to ensure that all of the metal parts are at the same potential. This reduces the risk of electric shock. Bonding is also required by the NEC. Electrical safety is a critical concern in any electrical system. It is important to follow all applicable codes and standards to ensure the safety of people and equipment. Regular inspections and maintenance can help to identify and correct potential safety hazards. Training is essential for anyone working with or around electrical systems. Proper training can help people to understand the hazards of electricity and how to protect themselves from electric shock. The NEC is a comprehensive set of standards for electrical installations. The NEC is updated every 3 years. It is important to stay up to date on the latest version of the NEC. Other applicable codes and standards include those published by the Institute of Electrical and Electronics Engineers, or IEE, the National Fire Protection Association, or NFPA, and the American National Standards Institute, or ANSI. These organizations develop and publish standards for a wide range of electrical equipment and systems.